Good evening, everyone, and welcome to the week 10 of the live sessions for the course Deep Learning for Computer Vision conducted by Professor Vineet. So, in week 10, the professor has discussed various concepts about generative models like variational autoencoders and generative adversarial networks. So, as usual, in this live session, we'll be first discussing few numerical problems, and then we will move ahead to discuss how to implement a generative adversarial network, in specific a DC GAN, which is nothing but a deep convolution generative adversarial network, and we will discuss it with the help of an example. Okay. So the first question talks about basics about VAEs itself. So as we all know that in variational autoencoders, we need to compute something called as the evidence lower bound, and we don't compute the maximum likelihood directly. Instead, we compute something called as the evidence lower bound. So what is the reason for such type of for such type of computation? The reason is given in one of the four options. So the first option says it is because the data distribution P of xi is unknown. The second option says it is because the posterior probability of P of z given xi is untractable or intractable. And option 3 just says only one is true. Option says both 1 and 2 are true. So here, one small detail I missed is xi is the input, z is your latent variable, P of xi given z is the conditional distribution, and P of z given xi is the posterior distribution. Okay, so the correct answer is both 1 and true. So this is true because first option, like we know, P of xi cannot be really computed, and P of xi is something. Oh, I think someone joined. Yeah. Hi. Welcome to the class. I just started with the first question. Maybe you can just take a time and look at the first question and just keep moving to the second question. Okay. So as I was saying that the first option, data distribution, is usually intractable in computing your variational autoencoders, and that is why the first option is true. And second option is nothing but the posterior probability, which again depends upon the P of xi, which is in the denominator of the posterior probability. So the second option is also true. Because of these two reasons, we can't compute the maximum likelihood directly, and hence we depend upon the evidence lower bound computation. Okay. Let's go to the second question. So, which of the following four options do you think is the correct loss for variational autoencoder? It's a very simple question. So, it's a standard loss function which we use in VAEs. So, maybe I'll just give you a second and you can guess the answer. Okay. So, the correct loss function is the first answer, first option. So the first option basically says that we have, so usually in VAE loss, we have something called the elbow computation, which, like I discussed previously, elbow computation is nothing but the first term. And we try to maximize this elbow computation, elbow loss function. Why do we want to maximize? Let's look at the first term itself. The first term talks about something called as the reconstruction error. So here we are trying to maximize the likelihood of reconstructing the x given a z. So if we are maximizing this likelihood, it means that the output x which we are recreating, it is very close to the input what we wanted. It's very close to what we want. So that is why maximizing the likelihood, it means like minimizing the reconstruction error. So that is why we want to maximize the first term. Now the second term is nothing but the KL divergence between your Q phi model, which is the approximate of the posterior, and the prior. Usually this prior P of z is nothing but um, it's most likely like a normal standard distribution, Gaussian distribution. So this is what we want, the KL divergence between the approximate posterior distribution and the prior. And we want this to be as close as possible. That is why when we maximize the entire term, we are indirectly minimizing this KL divergence. why do we need this to be close to each other? Because we don't want during the generation process that for each particular class, the latent in the latent space, the distributions are kind of spread out throughout the entire space somewhere in, like, small corners. We don't want that, because that is not very useful, because we want at the end of the day the space to be smooth between the classes. Like, I can easily translate from a smiling class images to a sad class images. There should be a smooth transition. So when you're minimizing the scale divergence, you're making sure that all of the latent classes that are being formed, the clusters or the distributions, are kind of close to each other, such that there is a smooth transition between the classes. So that is why the scale divergence is minimized and the first term is maximized to reduce the reconstruction error. Okay, I hope that's clear. If there are any questions, do let me know, and you can unmute and ask in between. Okay, let's move on to the third question. So here again, we're going back to the elbow part of it. So this is the loss function like we discussed, which is the elbow loss. So here we talked about there are two parameters, theta and phi. So phi is your encoder, theta is your decoder. So which of the following four options are true based on how do we optimize this parameters theta and phi? So just think about how, if you when we're minimizing this term, right, or maximizing this term, how will the parameters vary, and how we can use gradient descent to update these parameters. Okay, let me just discuss the options itself. So the correct answer is all of them are true. So let's just go option by option and we can discuss it. So the first option says that optimizing the theta parameters works very well using the standard gradient descent algorithm, which is true because theta, like I said, is nothing but the decoder parameters, and all these decoder networks can be easily updated by just taking the gradients of the loss and back propagating it. There's nothing much to do for the decoder part. The second option says that usually the problem comes when we are updating the encoder parameters, which are the phi parameters. The second option says that optimizing the phi is problematic as the gradient involves the expectation of the underlying distribution. This is exactly true because what we're doing is the output of the encoder or the phi parameters is nothing but mu and sigma. Mu contains the mean of the latent distribution, sigma is the standard deviation of the latent distributions. Now, if you directly use these together to create your latent vector z and then send this as an input to decoder, the problem is we are randomly sampling to create that latent vector z, and hence we can't really optimize phi because now we don't know which exact value what it was during this random sampling that was happening. So that is why second is true because optimizing phi is problematic directly. And option 3 says that reparameterization trick is proposed to solve too. This is exactly true. This is what was being proposed in the original paper, that instead of randomly sampling mu and sigma, they say propose that you have a simple element called epsilon, which will be sampled from a normal distribution, and then you scale this epsilon using the mu and sigma that you get from the output of the encoder. So that is a simple reparameterization trick, and with the help of that, now your mu and sigma is deterministic, and all the gradients will easily flow into the encoder, and the parameters phi is updated. So the correct answers are 1, 2, and 3. Okay. So let's move on to the next question. So this question is based on simple working of generative adversarial networks itself. So these are the five different options that are related to GANs. Which of them are correct? So it's based on the simple understanding of GANs. Okay. Let me discuss the correct answer and then the options. Yes, you're correct, Shruti. The correct answer is five. One, two, and three options are correct. So basically, what the first one says is the difficulty in training due to zero sum objective. That is exactly true. So, like we know, GANs, as the name suggests, it's an adversarial type of a training. And in adversarial, you usually have two components: minimum and min player and a max player. So you need to find a optimal solution where both the min and max player are balanced. So it's always a tricky part to do that, and usually that's the reason adversarial methods require a lot of time to train, maybe because of hyperparameter searching, optimal hyperparameter searching. Then the second option is also true. In vanilla GANs, there's a problem called as mode collapse. So, in a simple way to understand mode collapses, sometimes when you're trying to generate images and the discriminator tries to identify whether it's a real image or fake image, there's a problem that the generator might find a particular type of a image from a particular class, let's just say 0. So it identifies that whenever it is generating image 0, the discriminator is doing very bad at doing its job. So now what will the generator do? It will only keep on generating 0 so that its particular objective is being solved. It is fooling the discriminator and the loss is very, very low. But that's not what we want. There is no diversity in the images that are being generated. It's basically kind of like a loophole that the generator found out. So this is typically called as the mode collapse. So in this case, the mode is nothing but the frequency, or the, if you imagine the normal bell curve, the peak of that bell curve is called as a mode. So we want multiple modes to exist while generating, but if all of those modes collapse into one, then you're only generating one type of a image. So that's not what we want from a generating network. So that is why mode collapse is a common problem in vanilla GANs. Then third option is true again. Evaluating these generated images is a big problem. Actually, there should be a difficult word. Sorry for that. But yeah, what it means is that, like you, when you're generating these images, as of now, there are not many evaluating metrics available. It's mostly like IS score, inception score, or FID scores. Again, those have their own set of problems. It's still an active research area to get the most best metric for such type of generating of images evaluation. Okay, so the correct answer is 1, 2, and 3. Now let's move to the next question. So this is slightly, I wouldn't say a lot of, it's not a big numerical, it's a small numerical, but you still need to understand a little bit of how the equations itself work. So here we are saying that consider the GAN optimization, which is shown in the slide. Now let's assume that you have the true generator distribution, which is PG, and you also have the data distribution given to you, which is PD. Then what is the optimal discriminator? So this is the loss function. What will be the optimal discriminator, assuming that you have the true PG and true PD? I'll just pause for a quick minute, just try to solve it and let me know. Okay, let me discuss it then. So let's first look at the term which we want. We just want the optimal discriminator. So we'll just focus on this max of D for now. So let's expand the expectation. As you know, expectation is nothing but integration or summation of the probability of each of the element multiplied with the element itself. So that is the definition or the formula of expectation. So the first one, if you open the expectation, what will you get? Integration over x. Uh, what is the integration over PD of x, which is a true distribution, into log of d of x plus PG of x, which is the true generated distribution, into log of 1 minus d of x. So now, if you have to identify what is the maximum of the discriminator, just differentiate this equation with respect to d of x. That's it. So once you differentiate with respect to d of x, equate it to 0, and you'll get your max value. And the maximum value which you get is PD divided by PD plus PG. So what does this even say? So if let's assume that your input x is coming from a okay, before that, let's see what should be the optimal discriminator. The optimal discriminator is when it can identify all the real images as real by giving it a probability, by predicting the output to be close to 1. And it should also say that all the generated images are generated by giving it a label by with a probability of close to 0. So that is the optimal discriminator, right? The outputs for real images should be close to 1, and the outputs for the generated images should be close to 0. Now let's say the correct answer is this PD divided by PD plus PG. Let's say if X is coming from the true distribution, then in that case probability of D will be very very high compared to probability of G. Then this entire term will be 1. Then this is the optimal D of X, which means that D of X is equals to 1. That is what we want. Now let's imagine the opposite case. If it is coming from a generated image, the excess input is coming from a generated image, then P of G will be very high compared to P of D. Then this entire term will be close to 0. That's why, and this will be the output of D of X, optimal D of X, which will be close to 0, and which is the correct label for that particular input sample. So that's what this interpretation of this optimal value of the discriminator means. I hope this interpretation is clear and how we got this value. If there are any questions, do let me know for this particular part. Okay. Then let's move to the next question. So, like I said, there are some metrics that are available to generate the quality of the generated images of the generative models. So, which of these are the correct options that are used to calculate the quality of the generated models? So, they should be ID, not IS. Second option is Frechet ID score. Yeah, you're correct in pointing out. The correct answers are 1 and 2. These are the only two out of these four that are correct metrics for evaluating the generative models. So the first one is inception based scoring method. So in this, what we use the inception model, which is the standard CNN model, to calculate how diverse and how good the quality of the generated image is. Then the second one is called as Frechet ID score. So here we use the feature maps of the inception score. So we have both the real and generated images. We send them into the inception model. We get the output of the feature maps of these inception models. And then we calculate some statistics for both of these distributions. And then we evaluate how good my generated model is. So the second one, FID score, is more popular than the first one, and for various reasons, like it can give more better evaluation criteria compared to the first one, IS score. Okay, so these were the numericals which I wanted to discuss. Any doubts in any of it? If not, we can move on to the code part of it. Great, then let's move to the code. So today in the tutorial, we will be in the code walkthrough, we'll be basically discussing about a particular type of a GAN called DC GAN, which is nothing but deep convolutional generative adversarial network. So it is built on the simple idea of the GAN network itself, which is nothing but we try to generate some images from noise, from using that latent noise Z, we generate images, and the job of the discriminator is to identify whether these generated images are real or fake, and we try to maximize the discriminator, and we try to minimize the loss of the generator. In this way, we have a min-max type of a loss function, and hence the name adversarial network. So this is a bunch of different theory related to it also. You can read it on your own time, but it's the same what professor has discussed in the class. So this is the loss function, which you can see. So we want to maximize the discriminator, that is the D, and we want to minimize the generator, which is the D. And these are the two losses. This is the discriminator loss, and 1 minus D of G is the loss when we are sending the generated images. Okay. Yeah. So as usual, first we'll import the necessary libraries. I think by now you all must be very familiar with all these libraries. There's nothing new in these bunch of import statements. It's first we import certain standard Python packages like OS, argparse, and random. Then we import certain necessary torch packages like torch.nn, parallel, CUDA packages, CUDNN, Optim, datasets, transforms, etc. Okay, here we are manually setting the seed. So you all know the importance of seed by now. It is needed to reproduce the code, whatever you are writing or whatever anyone is writing. You need to set the seed to a particular value to make sure there is reproducibility. Okay. Then there are a bunch of different inputs that we will be using. So here we just described it. So I'll describe it as and when we go into the code. You can also look at each of the description at one place in this particular code block. The first one, data root, like the name suggests, it is the path root directory where the data set will be there. The second is the workers, as discussed in one of the previous sessions. Workers is related to data loaders. The workers will help you define or help you decide how many processes you want to allocate while creating the mini batches, or when loading the mini batch from the secondary memory to the GPU RAM. So all these things are handled by the number workers, and you define how many workers should be present in your particular program. That is what workers is defined over here. Then batch size, I think everyone is aware. We are setting the batch size to 128. Here we are using an image size of 64 cross 64. It's a RGB image, so number of channels is 3. Here we first define the size of the latent vector. As you know, the latent vector is what is given as an input to the generator, which will generate this 64 cross 64 cross 3 image. So we are giving a inputs latent size of 100. And we also have the size of the feature maps that needs to be generated, which is 64, because that is what the input image size is, 64. Sorry. Similarly, the size of the feature maps which will go to the discriminator is 64. That will be the input, and the discriminator basically reduces those feature maps to a simple binary classification output. 0 it is fake, 1 it is real. And here we're just training for 5 epochs. Learning rate, beta 1 is a hyperparameter for add. Number of GPUs, since we're using Colab, it's just one GPU that is available for free. Okay. So here we'll use something called as the celeb dataset, which is available in PyTorch. So let's look at the dataset itself, so you'll get an idea. Okay, these are a bunch of images of celebrities that has been created or scraped off the internet, and it has been created into this dataset. Very popular dataset for image generation. So I think you should definitely take a look if you're interested in this direction. It also is a very big dataset. Uh, yeah, yeah, it has around 1,62,000 images. So I think there is also newer versions of such type of celebrity datasets where the number of images are even more. So as usual, we first create the datasets from this particular celeb image. So we call this data dset.image folder. We mention what is the path we want. So .image folder is again a standard PyTorch library where you load your particular input data set by providing the root directory, and also you can do all type of transformations and augmentations by by mentioning it in the transform. So if you can look over here, what are the different transformations that we are doing? The first one is we are resizing original image. I think I don't remember it correctly. It is something 1024, but yeah, we are resizing it to 64. That is what the image size is. Then we are center cropping that image. So this is different from random crop. Like the name suggests, it random crop is it just randomly crops from anywhere 64 cross 64. Whereas in center crop, we are making sure that we crop only the center part of the image. In this case, why do we do that? Because most of the times the celebrity faces are kind of in the center, and we need to focus more on them. So that is why we do this. We do this center crop. Okay. Then next is transforms dot to tensor. Like I said, images by inherently are not tensors. They are, I think, in some other data types like uint or int8 or something. But we need to convert all those into tensor. So that is why this transforms dot tensor to tensor. Then we normalize this particular tensor, which is nothing but normalizing the pixels in each of these images. These are the different normalization values, mean of the three channels and the standard deviation of the three channels. Now, once you create your data set, next step is to create your data loader. So standard procedure, we just call data loader class and we mention which data set we're sending, what is the batch size. We need to shuffle the data here also. And then we need to mention the number of workers. Then you define your device variable. So say if you're using CUDA, then this device will point to the GPU, otherwise it will point to the CPU. And the small snippet that shows how you can plot sorry how you can plot the images. So this is a bunch of 64 128 images, I think. Okay, here we are regulating to 64. So we are printing the first 64 images in the first batch. Now let's go to the implementation of the network itself. So I'll just show you the picture first. So this is what a generator looks like. So we have the input latent vector z. This is then upsampled using conv transpose functionality. So you don't have to worry about writing that. You can use the PyTorch's inbuilt convolution transpose 2D class. So it will basically upsample your smaller spatial dimensions into bigger spatial dimensions. Like you can see, it goes from 100Z to 4 cross 4 comma 1024. Then it further enhances to 8 cross 8 to 512, further enhances to 16 cross 16 to 256. Finally, you get the output as 64 cross 64 and 3 channels. Now this will be sent as an input to the discriminator to identify whether this image is a generated or a real image. So first let's focus on the generator architecture, then we'll next look into the discriminator architecture. Before going into the architecture, there is one small thing. So in the official paper, they have mentioned a particular way to initialize the weights of this generator network. So usually we initialize it by default, whichever PyTorch is using. So PyTorch uses like Gulgrot or some function, which is a more standard, or Xavier initialization, which is more standard. But I think these authors have find a more optimal way for this particular GAN architecture. So that's why they mentioned it. So it's very simple to use it. You first create a small function called wait inits, and then you mention whether if it's a convolution block that you're encountering or a batch normalization block. If it's a convolution block, you just use nn.init.normal. So the weight initialization here is basically initializing it to a normal distribution with mean 0 and standard deviation 0.02. That's the only slight difference. Usually we use standard deviation 1, but here they use 0.02. So in this way, we just write the small function where you initialize the weights, and also if it's a batch norm, we initialize the weights data and the weights and the biases. So I'll show you how you can use this in the architecture, but remember that this function is custom created. We're not using anymore the standard weight initialization. Okay, so let's go to the generator class. As usual, first you create your class and import your NN module uh, parent class into this particular class which you created. Why? Because it points to the PyTorch code telling that this particular generator is nothing but a neural network. So there are two important functions. One is your init function, the first one. Second one is the forward function. As an init function, you define the architecture definition itself, like what are the different layers or what are the different global variables that you want. And in forward function, you basically define the flow of the data in that particular neural network. So what do we first define? We define the number of GPUs, which is one in our case. Then you define the architecture itself. So here I'm using something called as nn.sequential. If you remember in the first starting few classes, I told that there are two ways to write your neural network. One is using the sequential, where you write all your layers which you want in one go, and you can just call this nn.sequential. Like in this case, I'm just calling self.main, and you send the input, and the data flows one by one as however you mention in this sequential, and you get the output as the final answer. So this is when you know that you don't need any intermediate outputs or anything, or want to change or append or do anything in between. Then you can use the sequential. And the other way, it is more customizable, where you'll have to manually write or define each layer, and you have to manually define the data flow in the forward function, where the input is going to one layer and that output is going to the next layer, and so on. In this case, we don't need anything intermediate, so that is why we are using the nn.sequential. So what are the different layers? First, remember we're using everywhere convolution transpose 2D because we want to upsample. Our input is a simple vector. So we first have like 1, 2, 3, 4, 5. 5 transpose convolution layers. Each transpose convolution layer is followed by a batch norm and a redo. So, and the arguments for a convolution transpose remains the same. The first argument is the input channels, which is coming to the layer. The second one is output channels that you want to send in the output. The third argument is the kernel size or the weights matrix size. Fourth is the stride. In our case, the first one is stride 1. In between, we have strides of stride 2, and then again stride 1 and stride. Yeah. And oh, sorry, all of them are stride 2 except for the first one. And then the last argument is the padding. Padding is equals to 0 and 1. These are the two options which you have for padding. So these are the different layers that you have in your transpose. Obviously, you can play around in your generator. You can play around with the number of layers to see how good your generated images are and not. So in this way, you're creating these upsampling. It's the same dimensions, so you can look into the values to map to what are the dimensions. And finally, you get this 64 cross 64 comma 3. So our forward function is very simple in our case, because since we're using sequential, we don't have to worry about it. We just write self.main of whatever your input is getting, send it to that, and the output is returned from a generator network. How do we now apply the weights? You remember we created the weights, right? So if you just call the generator class right now, by default, all the default PyTorch weight initializations have taken place. But now you want to apply your particular part. So that is where you have this. So first you create an instance of the generator class, which is netg. Now we say netg dot apply weights initialize. So this is the function which we define. So that function will take care of whether it's a convolution class or a batch normalization class and apply the weights appropriately. So that's it. So make sure that you're initializing the function created is correct, and then you application wise, applying wise, don't worry about it. You can just write dot apply that particular function. Okay. Now let's print the shape or the architectures itself. So this is what you get. Convolution 2D transpose consists of the input will be 100. Like I said, it's 100Z, right? The input vector. Then the output is 512 channels. For the second one, convolution, input is 512, output is 256. Similarly, 256, 128, 128, 64. Finally, the output number of channels is 3. Appropriately, the sizes are also, the size will also keep on reducing. Sorry, the size will keep on increasing in transpose convolution. Let me quickly pause. Any questions before I move on to the discriminator? Any part that is not clear in the generator network? It's more or less the same CNN architecture. The only difference is we used transpose convolution instead of a simple convolution. Okay, great. So if there are no questions in the discriminator part, let's move on to the generator part of it. So generator, like we said, it's a simple binary classification network which will take in some input images, sometimes real and sometimes fake, or is generated, and it has to output whether it's a real or a fake image. That said, let's directly jump into the architecture. I don't think we have an image, but it's a simple architecture. So here again, we define the class discriminator, import the nn dot module, two functions init and forward. Here also we don't need any intermediate values, so we just create the sequential type of a neural network. So what are the different layers? We have one, two, three, four, five. Five convolution layers, and these are normal convolution layers. Why? Because we now want to downsample from the input image to a simple one value output where we say whether it's a zero or one class. So that is why we are using simple convolution. And after the first convolution, we don't have batch normalization, and here we always use leaky ReLU. It's a slightly different version of ReLU. The difference is, in leaky ReLU or in normal ReLU, any value which is less than 0, the output will also be 0. In leaky ReLU, any input value which is less than 0 will have some small negative value. That's the only difference between ReLU and leaky ReLU. And then finally, you output dot sigmoid. It's basically saying that your activation function is squashing all your input values to either 0 or 1. That's what we need. We want it to either go closer to 1 or closer to 0, depending upon the input. The process again, you just have to, the arguments remain the same. First argument for convolution is the input channels. Second is the output channels you want. Then kernel size, stride, and padding. Bias is all false. You don't have to put it true. Then you define your forward function, which is nothing but sending the input to this particular discriminator and you get the output. Here also we apply the weights, like I said, custom weights, which is normal distribution with mean 0 and standard deviation 0.002. We do it the same way. We first create an instance of the discriminator and then we apply the weights. Okay. One part I might have missed in generator, this parallel. Don't worry about it. This is if you have multi GPU and if you want to parallelize your network to utilize all the multiple GPUs. In our case, this won't execute because we just have one GPU. But if you have the compute power of multiple GPUs, do check it out how fast. Maybe you can do analysis on your own, how much the training time has reduced and all. Okay, now let's look at the output of the discriminator network itself. Starts off with 3 channels and goes to the 512 channels. Finally goes to one channel output, which is then sent to the sigmoid activation, and that is what you get an output between 0 and 1. Okay. Now let's move on to the loss function itself. So loss function is basically it's like binary cross entropy loss, and we specify binary cross entropy is this equation: minus of y is the ground truth value, xn is the input, minus of yn log xn plus 1 minus of yn into log of 1 minus xn. So what does this mean? So let's say if your image is coming, if your image input image xn is of a true class, then this yn, this particular part of the function will execute. This particular part of the loss function will only be activated because 1 minus of the true class, which is 1, this will become 0. So now we are forcing that the input predictions should be close to 1. Similarly, if your ground truth input is belonging to class 0, the first term will go to 0. The second term will now get activated, forcing your model to only predict the output 1 minus of the whatever output you're getting, sigmoid output. That value should be closer to 0 because the ground truth class is 0. Same thing here. Now we have d of x, which is the output prediction for the first one is of the real class. So the first one will have log of, instead of xn, we'll have d of x, which is of the real class, label 1. Similarly, the second term will have 1 minus of d of g of z, which is the generated image. So that's the only difference. Replace in the first term x with d of x. The second term replace x with d of g of z. remaining all loss function remains the same. Now let's look at it. So here we use a simple binary cross entropy. That's what we are calling it as criteria. And then, yeah, we create a batch of the latent vectors that we can just use to visualize how the generator is getting progressed and all. That is what this fixed noise is. Now we have to first create real label, because by what do you say, inherently we don't have any data set like fake label, right? So we have to manually create the labels for ourselves. Everything that is coming from the original data set is given a label 1. Everything that the generator is generating, we create a manual fake label called 0. We have two different optimizers, like I told, it's a min max type of optimizing. So both of them will have their individual optimizers. uh, Both of them are Adam optimizers in our case. Okay, now let's look at how we are training. So we first train the discriminator, then we train the generator. So yeah, let's look at how we are going to do both of them. You can the code, see, the text is the same what the professor has discussed. It's just written for you to get more understanding, but let's look at the code itself. That's more important. First, you'll define some bunch of empty lists. This is just to keep track of what are the image list, or what are the losses of the generator, or what are the losses of the discriminator. And this is iters basically keeps track of how many iterations are done. Then you have two for loops, like as usual whenever you do for any type of neural network training. The first for loop is across the epochs. The second for loop is across all the batches in your training data. Okay. Now, first part, we maximize the discriminator network. How do we do that? We first train with all the real batches. So here we'll have three different. First, we train it with all the real batches for the discriminator. Then we train with all the fake batches. Then we update the G network also, which is the generator network. So here we have like the same update equations which you usually write for other neural networks, right? What are the 5 steps or 4 5 lines which I always say? Have the zero gradient, do a forward pass, calculate the loss, then do the backward pass and the step. These are the 5 things, 5 steps which you always write for any neural network training. So we follow the same thing. Here we write it 3 different times because we do it for 3 different types of, actually 2 different types of input network inputs and 2 different types of networks. So total we write 3 times. Let's look at it one by one. First one, train with all the real batches. So we first initialize the discriminator to have zero gradients. We take the real data, which is from the mini batch which you're getting, and then we make all the labels. We create a labels over here, which is all ones with respect to the batch size. In this case, it is 128 labels. Then we do a forward pass through that discriminator, and then we calculate the loss. And now this loss is propagated backwards. That's it. Sorry, yeah, this loss is propagated backwards. And now we calculate d of x, which is nothing but the output mean of this particular discriminator. Now let's look at the fake batches. Just a minute. Yeah, sorry. So how do we train the discriminator with the fake images? You first create some random noise. This random noise needs to first go to the generator. That's why we are first sending it to the generator in XG. This is what we call the fake images. We then create the labels, which is all zeros. Now we send this fake images as an input to the discriminator. Then you calculate the loss between the output of this discriminator now which you just got, and the labels which you just created, which is all zeros. Okay. Then we calculate the backward loss, we calculate the dot backward for all the fake error values of this discriminator, and then we calculate the mean of the fake losses also. Now the total loss is nothing but the sum of these two losses, and then we do the weight update of the entire D network. So if you remember, if you can see, the weight update happens only after you calculate the forward pass of the real images over the discriminator and the fake images over the discriminator, calculate the losses, take the mean of both the losses, sum them up, and then you update your weights of the discriminator. So in this way, you're maximizing your discriminator network. Next is how do we update your generator network. So let's look at it. Here again, you initialize your generator network to zero gradients. create a bunch of labels. Yep. And then here we create again the forward pass, not create, sorry, we do the forward pass. We send the fake images to the d of x, and now this particular output is then we calculate the loss with the help of this output and the labels, and then we calculate what is the backward of this particular error, calculate the mean of the loss, and then we do the gradient update. So, and rest of the steps are nothing but it is simple, just keeping track of all the losses, just appending them into these uh, empty lists which you just created, and just printing statements. So this has nothing to do with the training part. So if you look at the output, this is what the output you see. So we are running on the leftmost side. What you see is epochs. We are running for 5 epochs, and here what you see is the number of batches that has been created. There are 1500, roughly 1583 batches that has been created, and each batch is of 128 size. And after every batch, this is the loss which you get: loss of the discriminator, loss of the generator, and yeah, these are the values which you're getting. I keep on training. I'll just show you the visualization part. So as you can see, initially the generator loss will be high, and then the loss keeps on decreasing. Whereas the discriminator loss always has this pattern. It keeps on wobbling between, certain range of values. It's never really decreasing. That's what you need to find the balance. That's what the optimal balance that we need to find in adversarial learning. Now let's look at the fake images that were created. Obviously, we used a very simple GANs, and uh, also we didn't train it for a lot of epochs. We just trained it for 5 epochs. And still, you can see from the fake images that it was able to generate decently. Like there are certain off things that are there in every image, but still, it was able to capture a certain type of correlation, like eyes, mouth. It was able to place all of these in a certain way in the face. It's not like eyes are coming somewhere randomly. Like there are certain images like this where it is completely bullshit, but for some images, more or less, it is still having the placement of the human features correctly. Yeah, you got to realize that this is just coming from a random noise vector. So going from a random noise vector to such type of images is still a great thing, but obviously nowadays we have much more advanced. I think in week 11, if you see diffusion models, they are way more hyper realistic. Even GANs have done, like SR GANs and all, photorealistic type of images, but you can definitely go through diffusion models, which we'll discuss tomorrow. They are much more advanced in generating all these images. Yeah, so that's what I wanted to discuss in today's class. Any questions or anything? Anything in the code or anything in the numerical problems, MCQ problems?